Hello everyone, I am Dr. Dan-asabe. We shall continue with our lecture, Engineering Metallurgy. Here is the outline. We're going to look at equilibrium phase diagram. These are the types. These are the specific materials used. Cupronickel, lead, tin, aluminium, silicon, brass, bronze. And we also have iron carbon phase diagram. These are the materials used in producing these lecture notes. Equilibrium phase diagram. It's a phase diagram that represents the relationship between temperature, pressure, and compositions. Many microstructures develop from these phase transformations. This may involve transition from one phase to another. The phase diagram is helpful in predicting phase transformation and resulting microstructures which may have equilibrium or non-equilibrium character. These are the types of equilibrium phase diagram. We have the unary type and binary phase diagram. The relationship here is pressure temperature for unary, and for binary it is temperature composition where the pressure is kept constant, and here the composition is kept constant. So let's start with the unary phase diagram. Here it involves only one substance, a pure substance. An example is water. The relationship is pressure and temperature. And here it has three phases: solid, liquid, and vapor phase. This is the triple point where all the three phases coexist. This is the point where you can have transformation from solid to liquid at 1 atmosphere at 0 degrees. Here at equivalently 100 degrees, you can have transformation at 0.3 from liquid to the vapor phase. And here the second type is the binary phase diagram. So we have three types. Let's begin with the first one, binary isomorphous system. Isomorphous in the sense that here we have three regions: the solid region alpha, the solid alpha plus liquid region, which is the sticky region, and the liquid region. It is isomorphous in the sense that all through here nickel is soluble in copper, so you see only a single phase. And here it says that alpha phase is substitutional solid solution consisting of both copper and nickel atoms. Here it means that in the crystal structure, nickel atoms can substitute that of copper atom to form an alloy, and this is because both nickel and copper have similar crystal structure, which is FCC, identical atomic radii, electronegativities, and valencies. Here we have, as I said earlier, a three-phase region: liquid, the solid region, and then the solid and liquid region. And these are the primary key 3 points needed in interpretation of phase diagram. So let's look at them each. First is the phases present. For an example of binary isomorphous system of copper and nickel, binary in the sense that we have copper and nickel, two materials or two substances. For example, at point A, the phase present is the alpha phase. At point C, the phase present is the liquid phase, and at point B, the phase present is the alpha plus liquid phase. So second is determination of the phase composition. At point A, the composition at A is 60%. It corresponds to 60% nickel and 40% copper. And normally the one identified here, written here, is the composition that changes, while the other can be gotten by subtraction from 100%. Here it means at this point copper is 100%, and nickel just begins to increase from 0 up to 100%. Here nickel is 100% while copper is 0%. So at A we are able to determine the composition. At point B, the composition can only be gotten by drawing a tie line. This is a tie line, a horizontal line that touches this line, the liquidus, and then this line is solidus. So the composition here can be gotten at this point where it touches the liquidus, which is 32% nickel and 68% copper, and the solid composition alpha is 43% nickel and 57% copper. And then third key point in the interpretation of the diagram is the percentages or fractions of the phases. This is usually important when we have a dual phase region. We want to know the percentage of each. So this is it from the tie line here. If you want to know the fraction of the liquid phase at B is going to be S all over the total, which is R plus S. This is it. And then the fraction of alpha here at B is going to be R all over R plus S. And these are given from the identification here. Cl, C naught is our original alloy, and then C alpha, and we can be able to get them as 0.68 and 0.32 fractions of the liquid phase and the solid phase. And this is just explanation. This is an explanation of how to determine the fractions, the phase amounts. Here, when we have a binary isomorphous system, here it will be other systems also, where instead of the liquid we have alpha plus beta. So the volume fraction is going to be this volume of alpha over the total volume alpha plus that of beta. And this is also equal to, when you add the two volume fractions, that of alpha and beta is going to be equal to 1, or 100%, excuse me, in percentage. This equation is useful when we already have our result in a weight fraction of alpha and beta, and we want to convert them into volume fraction. So this is it. And this is also useful when we have our initial result in volume fractions and want to convert them to weight fractions. Here it is said that phase volume fractions are preferred because they may be determined from examination of microstructure. Yes, this is true because the phase volume fractions are proportional to composition, linearly proportional to composition, unlike the weight or mass fractions, which are not linearly proportional. And that is why it makes it easier for the composition in volume fractions to be used to estimate the microstructure of the alloy as the composition changes. Here it shows that when we have density of the two substances are the same, then it means the weight and volume fractions are going to be the same. So here, when you assume the densities are the same, it means the densities will cancel out and weight fraction is going to be equal to volume fraction. Now here we look at development of microstructure in an example of isomorphous alloys, that of copper and nickel. Here we have at point A here is completely liquid. As it goes down vertically, it is cooled down to B. Here it is virtually still liquid, but the solid alpha has just begun to form, though it's virtually almost 99.9% liquid. So as you move to C, the alpha has formed substantially here, and then the composition of the alpha is going to be 43% nickel, and that of the liquid is going to be 32% nickel. As you go down D here, it is virtually solid here, almost 99% solid, with composition of the alpha to be 35% nickel, and that of the liquid, very negligible portion, to be 24. This is just the composition, not the volume fraction of the liquid. It's only the composition of the liquid here, which is 24% nickel. And as you move down, as you cool down to E, it's all the remaining liquid has completely transformed to solid alpha. This is the further explanation of it. But here it's saying that in practical solutions, in practical scenario, we may not have this in this case, because in practical form it is it is not an equilibrium phase. There may be a little bit of alternation from this diagram in practical sense. This is the mechanical property of the isomorphous alloys. This is telling us that The advantage of alloying here, when you add nickel to copper, you can see the substantial increase in strength, almost double the strength of the tensile strength of copper. Though there's a bad drop here, we have a drop in elongation, but then if you look at it holistically, it is still worthwhile. Here is another type of the binary. Here we call it the binary eutectic system. Here we have still two materials, two substances, copper and silver. We have, in this case, we have three single phases, alpha, beta, and the liquid phase. We have three dual phases, alpha plus beta, alpha plus liquid, and beta plus liquid. And this is called the eutectic point, where we have a direct transformation from liquid when there is cooling to solid, alpha plus beta, or when we have heating from this point, from this region to this point, it transforms from solid to liquid. This is called the eutectic point, and this is called eutectic temperature, which is 779 degrees centigrade. And we also have the solubility limit here. Here it means here it's 100% copper, so it means in this region the amount of silver in it is soluble. As you move from this region to this region, the silver is no more soluble, and so you have alpha plus beta. Here at this point is almost 100% silver. Here this region beta, there is no much difference between the beta and 100% silver. So, but the copper in here is soluble. But as you move from this region to this region, this copper in there is no more soluble, and you have alpha plus beta region. This is called the solvous, and this is called the solidus. This is called the liquidus, the line from liquid to this sticky region, alpha plus liquid. So here is still an explanation of the binary eutectic system, which we have done. This is development of microstructure in the binary eutectic system. Here, if you look at the far left of the diagram, from liquid here, when you go down cooling vertically from A to B here, in the B here we have the two-phase region alpha plus liquid here. From liquid here to B, the solid begins to form, and as you come down, complete solid at E has formed all through, which is a single phase. When you move rightwards a little bit here, you have from liquid, from point D, as you go down vertically, E, you have the solid begins to form, and as you go down vertically at F, all liquid has completely transformed into the solid alpha, and as you move from F to G, beta begins to form, and you can see beta forming in G, this phase, because this is the region of alpha plus beta. But as you move down, more of beta is formed. Here you can it says that these particles will grow in size. It means beta will grow in size as you move down from G downwards. Let's assume this is a point here. You want to understand this better, you draw a tie line here and determine the percentage of beta, and the tie line here determine the percentage of beta. You find out the percentage of beta at this point is greater than the percentage fraction of beta. Here, this is the eutectic point, or we call it the eutectic structure, or when you transform from liquid directly by cooling to down here, this is the structure you are going to have. We call this the eutectic structure, alternate layer of alpha and beta, and you can determine the composition here by drawing a tie line. Here alpha is going to be 18.3 here, a little bit down, and here is going to be 97.8% by weight tin of beta. So as you move a little bit left from the eutectic structure here starting from Z going down H, assuming the alloy composition is C4. Here from liquid, you come here, you have alpha begins to form, and as you go down, as we explained earlier, more of alpha is going to be formed. This is it, alpha begins to grow, the weight fraction of alpha begins to increase. As you move just below the eutectic temperature, all the remaining liquid will now transform to eutectic structure. So all the region of the liquid will now completely transform the region of eutectic structure. In this case, you have two types of alpha: the primary alpha and the eutectic alpha. That's the alpha in the eutectic structure. And then you have beta. Similarly, when you move rightward here, you are going to have something similarly, but in this case, these bigger circles are going to be beta in blue color, and then this you have also the eutectic structure. But in this case, you have two types of beta also when you move right: the primary beta and then the eutectic beta. These are example questions. We look at them. So let's look at the solutions to these examples. So let's look at the solutions to these examples. So this example 1, we are asked that this is the composition of the alloy is cooled just below the eutectic. So this is it at 34.6% by weight tin. So this is the point, 34.6%, just below. So this is the point. We are asked that it is cooled. We are asked to find the fraction of the eutectic alpha and eutectic mixture. Eutectic mixture is here, so we draw our line here, and then where it touches here, we draw the composition here, C alpha. So here at B, it is a mixture of peritectic alpha and then the eutectic structure. So the fraction of the eutectic structure is going to be R all over total R plus S, and that of the peritectic alpha is going to be S all over the total R plus S. Excuse me. So this is the fraction in weight percentage, which is that of peritectic alpha, which is 0.64%, and this is that of the eutectic mixture, which is 34%. Well, let's look at the second question. Here we have 40% by weight tin and 60% by weight lead at 150 degrees. So let's locate this point. This is 150 degrees, and we go down at 40%. This is the point. So we are asked to, the first question is, what are the phases present? So the phase present is alpha plus beta. So this is within the alpha plus beta region. Alpha and beta coexist. And then what is the composition of this? What are the composition of these phases? So here we are asked to find the composition of the alpha and that of the beta. So in this case, we draw the tie line here. The composition of the alpha corresponds to this, which is 11% by weight tin and 89% by weight lead, and that of the beta here is given by this point. And then we are asked to find the weight fraction of alpha and beta. Weight fraction of alpha here is going to be S all over the total R plus S, and similarly that of beta is going to be R all over, weight fraction of beta is going to be R all over the total, which is R plus S, and here they are gotten as 67 and 34%. Here we are asked to find the in terms of volume percentage. So this is the formula we are going to use, but here the density of alpha and beta are not exactly the same thing as density of lead and tin. If you look at it from here, the region density of alpha is an average of lead and tin, and density of beta is also an average of lead and tin. So we have to use this equation to determine the density of alpha and beta. Here is the concentration of alpha, a concentration of lead at alpha point, and that means concentration of lead at this point, concentration of tin at this point, and concentration of lead at this point. So this is given as concentration of tin over density of tin plus concentration of lead over density of lead at the point alpha. So similarly, that for beta can be determined here as 7.29 grams per cm cube, and then we substitute into this equation to be able to determine the volume fraction also, and then converted to percent, which is 58% and 42%. The third question here, it says the mixture of lead tin alloy at 180 degrees and composition. Though we don't know the composition here, we are told that the eutectic we are to consists of primary alpha and eutectic structure. So this is it, primary alpha and eutectic structure. So we know that it's going to be within this region. From here, the eutectic region, and then here, this is where it touches it 180. We don't know actually the composition of the alloy composition. This is what we are going to find. So, but we are given the fractions of the alpha, pro-eutectic alpha, and that of the eutectic mixture. So in this case, we now say fraction of the eutectic alpha is going to be what? S all over the total, R plus S, and we use these points here to further elaborate. So it's going to be RS all over the total, R plus S, and in this case we substitute. We are already given the fraction, and then we can be able to find C1 by making it subject of the formula of this equation. Similarly, we can use the other way around using the eutectic mixture, which is 4.43, to be able to determine the composition of the alloy. So the composition of the alloy is given as 36.98% by tin and 63.1% by weight lead. We come to the end of this lecture. Thank you for listening.